Hi, this is the lecture in the DIC course where we discuss the power of MOS device. The power of MOS device can be divided or classified to be either dynamic or static. The definition of dynamic power, it is the power dissipated due to activities on the circuit, and we can generally say that it is either switching power, okay, this is switching power, or short circuit power. The switching power is due to discharge and the discharge of the capacitance at the output node of the uh, CMOS gate, while the short circuit it is due to the current that flows from power to ground during the short time when both the NMOS and PMOS are active. Static power, we have three types: subthreshold, uh, or gate leakage, or junction um, leakage power. In this lecture, we are going to start with the dynamic power, and next lecture we will address the static power. The summation of dynamic power and static power contributes to the total power dissipated by the CMOS circuit. The interesting part is that for current processes, static power seems to be increasing more and more as dimension of the devices are reduced. More of the leakage current increases, causing more of the leakage power and static power. So this is more of a very um, important as well, not to be ignored, especially for modern processes. Okay, so let's consider, for example, the operation of we probably can suppose, for instance, we would like to um, uh, we measure the power of a system versus time, and the system power goes up and down. In this case, we define energy to be the integration. Let's say, for example, it is from time 0 to time 1. The integration from t0 to t1 of the time-dependent power, okay, and the average power, and of course, this in the diagram, this is computing the area. So the area under the curve would be our energy. And the average power in this case will be dividing this energy over the time period where t equals t1 minus t0. Now, this is the average power, not to confuse it with the instantaneous power. So, for example, let's just say at this time here, the instantaneous power is this value, okay? But the overall, the average power is when we divide the total energy over the period of time. So um, one of the things that we like to tie is the while we are discussing this power issue is that um, would like to let's see if we move the slides a little bit here. I'd like to share with you the power consumption of typical households, and I do understand that this is electronic course, and but the principle applies even for the appliances. These are typical appliances at home, average values. Say, for example, you have a ceiling fan, and average values of the power consumption is 60 watt to 70 watt. And if you look at, for instance, inverter air conditioning, seems the recent ones, it is from 1.3 kilowatt to 1.8 kilowatt, substantially higher compared with the fan. Um, the cloth dryer, okay, and you can see up to 4K watts, and the purpose here is to raise the awareness of the devices that are in our home and consuming a significant amount of power. So if you for instance have in your home a refrigerator which consumes 200 watt, and you have one refrigerator and you turn on this device 24 hours, and let's just say this is 20 watt that all the time it consumes. I do understand that the refrigerator and other devices go into cycles of operation, but for simplicity, let's say it consumes 200 watt all the time. And in this case, your refrigerator will consume, if we multiply average power by time, we will get the energy. So if we would like to get the energy per day, so I have one device which consumes a power of 200, one device times 24 hours. That would give me the total wattage per hour that I consumed during the day. And if I multiply it by 30, that seems to give me the just pick a different color here. That gives, or that provides the kilowatt hour per month. Bear in mind that kilowatt hour here is an energy unit. It is not power unit. Okay, so when I divide the whole quantity over 1000, this is my consumption, 144 kilowatt hour of energy that I consumed per month for this device. Now suppose I have an AC air conditioning which consumes 1.5 kilowatts. I have one of those in my house and I turn it on for 4 hours only, and so this is the amount of power, one device, amount of hours, and 30 days for a month. Divide by 1000 to convert it to kilowatt. So that device will consume 180 kilowatt hour per month. So if you go down the list here with these devices, you see that I have, for all these devices, for instance, consumed 648 kilowatt hour worth of energy. So this is energy, by the way, total energy. Okay. Um, Now you look at the electricity bill here in Jordan, and you will see and in everywhere actually, you will see that the calculation of electricity bill goes into certain brackets. So if your consumption per month from 1 kilowatt to 160, then this is the price. 161 to 300 kilowatt hour. This is the price. So since we have 648, we are covering this bracket and this bracket and this bracket and this bracket and all the way even up to this bracket. And we compute our consumption. So for example, we are going to have the entire bracket. So we have 160, 160, 160 kilowatt hour times the price per kilowatt hour, and that comes to 5.28 JDs. And now we also cover the second bracket, which is 161 to 300, and we multiply this by the price. Notice that we don't double the previous period, so we have to subtract 300. So this is like the range. Okay, so you multiply the range by the price, and you get 1008 JDs. And then here we compute the range, which is right here, and multiply it by the price, which is right here, and we get 17.2. And also we cover this entire range, okay, and times 0.114, that comes out to be 11.4 JD. But this range right here, we don't cover it all. We cover up to 648. So we subtract 648 minus 600 times the price of this range, okay? And that turns out to be 7.85 JDs. And obviously we are not at this bracket because we are less than 700 and 1000. So we ignore calculations here. So we plug in zeros and we add all the numbers here, okay? And this turned out to be 51.544 JDs. And this is how they compute our utility bill for the month. Okay, so keep in mind that these are examples figures, okay? So they are not real numbers are different, but I just want to show you how we compute those for the electricity bill, okay? Now, and just a reminder here is that the devices that we deal with are either a power supply, okay? And in the case of the power supply, the power equals the current produced by the power supply times the voltage of the power supply. So this is okay. And for a resistor, the power equal. So this is PDD. The power for a resistor, it is the current times the voltage. Okay, so it is V times I, and for the resistance, and you can replace one of them, you get one of these two equations. For the capacitance, okay, you integrate the current and voltage, okay, for the capacitance, and we will see in the next example how we compute this integration. As we have indicated earlier, that the CMOS circuit power is dynamic and static, and we looked at the various components of those. So right now we are going to look at the um, uh, switching power of a CMOS device. And let me just take this. Okay, that's not what I intended to do. Um, Let me go back here, and I want to explain this in. Okay. So suppose I have now uh, myself here organized slightly. Suppose I have an inverter, and this inverter is driving a capacitor here. So this is right here. Um, um, this is the C load here, okay, and this is my output voltage, and this is my VN, and this is my VDD, This is my VSS ground. Now, suppose initially, um, I have V out equals 0 volt, and I switch the input here. Let's say, for example, the input is switched. Okay? So this is my volts and the time. So let's say the input has switched from 1 to 0. And what this will lead to is that our output voltage will switch from 0 to 1. So this is my Vn and this is my V out. And clearly when the V out, so this is here 0 volt and this is here VDD, okay? And clearly that the capacitor is charged. Now, there are two things we would like to compute. First, energy drawn from power supply. And then energy, second thing is energy stored in the capacitor. The energy drawn from the power supply is computed, we refer to it as VDD, by integrating, okay? So we have this current basically that is going to come from VDD, and this is where we integrate this current. And we know all the time my power supply will have always VDD. It will provide a potential of VDD all the time, DT, okay? And the current here is the capacitance equation, which is I can replace it with CL dVt over dt, okay, VDD dt. Let's just change the color here to illustrate some of the, so notice VDD here stays the same, okay? What we did, we just replaced, okay, all right? You do this integration and you will end up, if you compute it, you will end up with CL VDD square. Now, for the energy stored in the capacitor, it is the similar integration, but now the potential across the capacitor is not fixed. It is rather actually VC. Okay, and if you replace this equation here for the current, it will be CL dV over dt V dt. Watch the cancellation here, okay? And we end up with the result equals to half C VDD square. Now, look at the interesting result here. The energy from the power supply is CV square. The energy stored in the capacitor is half CV square. It's kind of interesting. So, for example, if we are giving 1 femtojoule or 1 picojoule, okay, from the power supply, somehow that picojoule, half of it is stored here, okay, and the other half is gone where? Well, and actually it is it is dissipated as heat in the PMOS transistor. And when we discharge the output, and when that is going to happen? Well, this will happen when we change the input. Okay, and you see that the output will come down, all right, and we will discharge the output. This is when whatever charge on this capacitor will be discharged to VSS, and we will burn it as heat in the NMOS. So there is a part which is dissipated as heat in the PMOS when we charge the capacitor, and there is a part which is dissipated as a heat in the NMOS capacitor. And this is when in NMOS device, this is when we discharge the capacitor. Okay. Now, there's an interesting here. Let's go back to the presentation. There's an interesting diagram here where it shows here is a device here, an inverter, and we have the input to the inverter. So this is the input, which is right here, okay, and this is the output, and which is right here. Notice how the input goes from high to low to high, and therefore the output goes from low to high to low. Watch the current in the PMOS device. They are fixing the time scale here for all the figures, so we can correlate events. When we are charging the output, we have a current through the PMOS device. When we discharge the output, we have a current through the NMOS device. Watch the power dissipated, okay, in the PMOS device, the power that goes through the PMOS device, and the power that goes through the NMOS device. And this is during charge for the PMOS, discharge for the NMOS. I want you to look at the current in the capacitor. This is here, the current in the capacitor. When we charge the capacitor, we have a positive current going to the capacitor to charge it, and then a negative current to discharge the capacitor. This is the amount of power that we are charging in the capacitor and amount of power that discharges the capacitor. Watch how this energy profile increases in this capacitor here. When we discharge the capacitor, just up here, and then we discharge it. The discharging happens when the output is discharged. Okay. Watch the current here from the power supply, and this is the energy that comes from the power supply. And the interesting here, there's a different profile from the energy and the load. The energy that comes from the power supply, it is taking from it and stays at the same level, but the energy in the capacitor is half of that amount, and also it gets discharged, right, when we switch the input. But whatever energy we draw from the power supply, it doesn't get discharged. We take it one time during charging of the output. So we take it from the power supply, and that's it. Never goes back to it, unless you are talking about energy harvesting techniques, and this is not the topic here. While the energy on the capacitor is stored halfway through, and then it gets discharged whenever we discharge the output. So this here, okay, is half this quantity here. Okay, so he's saying that assume that we have a VDD of 1 volt, a CL of 150 femtofarad, and a frequency of 1 gigahertz. Okay, and that the energy, which is the CV square comes to 150 femtojoule stored, or I should say, drawn from the power supply. Okay, so 150, okay, femtojoule will be drawn from the power supply, and 75 femtojoule will be stored in the capacitor here, all right, which is half of this quantity. Okay, CV square, half CV square, and the other half, so we will draw 150 femtojoule, 75 of those 50 joules stored in the capacitor, and 75 are dissipated as heat in the PMOS. And then when we discharge the capacitor, when the input changes, we will discharge those 75, 50 volt as heat in the NMOS device. Okay? Okay, so this is basically the switching power. Uh, and and Okay, so after we computed the energy, the question is how do we compute power for the device? And as we have indicated earlier, that power, dynamic power, which is our focus right now, can be switching our short circuit. And so now we are concerning about, or we are trying to compute. Whoops, we're trying to compute the power. Okay, so I'll put this in presentation mode. Compute the power dissipated charging and discharging this output capacitance. So it is a switching power that we are doing. Um, so we understand that the energy drawn from the power supply is equal VDD square times CL. So to compute average power, basically um, dissipated by this power supply, we say that power equals the energy, right, over here, which is V square VD times CL, and then we need to divide this quantity by the period, and this is the period. Will take it from the clock period, and it is basically the clock period of the system. But there's an implication here when we divide by the clock period. The implication is that we are doing a charge every period, every clock period, and this will lead to V square times CL times frequency. This is the power dissipated switching, so we'll call it switching power, switching this device. But there is a condition, which is we do charge and discharge this capacitance every clock. This seems to be a very strong condition for most of the nodes in the design. It is true for the clock node, though, but not for all the nodes. And that is why what we need to do is that we say, wait a second, not all the nodes are charging and discharging all the time in the system. So we need some kind of activity factor. This activity factor is set for one for signals that are active, like the clock signal, but signals that are not active, they will have less activity. In fact, most of the signals in the system are not very active, um, and they switch every once in a while. So the activity factor of one is reserved, excuse me, reserved for the clock. And for those signals that switch once per cycle, they have activity factor of half. Okay, so we have somehow plug in this activity factor in our equation to get more realistic switching power for nodes. Okay, so we said dynamic power can be switching or short circuit. And now let's talk about short circuit. Short circuit, it is when the PMOS and the MOS, for a very short time, both of them are on, which causes a current to flow from the power supply to ground for a very short time. Typically, this is really ignored in the systems because yes, it is there, but we are doing a very good job at having sharp input and sharp output, or let's say rise and fall times for all the nodes. And so these type of power drainage are uh, ignored compared to switching power. The dominant of the dynamic power is the switching power. Short circuit typically are less than 10% and ignored for calculations or added later on as a extra estimate. So for the purpose of this course, we will ignore them. Okay, so here I have a system where I have a system of 1 billion transistor. So this is the system here. I have a logic 50 billion here, so 50 million, sorry, million um, gates, transistors, sorry, and those are logic. And then I have 950 million of memory. Okay, so typically, by the way, logic circuits, logic transistors are more active than memory circuits or transistors. So you can see the activity factor is 10%, and here is 2% for the memory. Okay. Now he's telling me here that for these transistors, the average width is 12 lambdas, and since I'm doing in my textbook, lambda equals 25 nanometer. Okay, and he's saying that assume VDD is this value, and for every micro we are going to assume 1.8 femtofarad for every micro of the gate or of the transistor. 1 femtofarad of those for gate capacitance and 1.8 for the diffusion. Now, of course, now for my let's see if I can pick a color here for illustration. Um, Now for my computation of power, okay, I know that power equals what? Um, activity factor times capacitance times V square and F. Well, V square he gave it to me, which is 1 volt. F gave it to me as 1 gigahertz, right? Which is right here, 1 gigahertz. Okay, and this is the voltage right here. Okay, all right, so I'm done. It is the problem of the activity factor times the capacitance will be a little pain, because I'm gonna have I have one specific activity factor for the logic and a specific activity factor for the memory. And now what I need to do is to compute the capacitance for the entire logic and then multiply it by its own activity factor, and the capacitance for the memory and multiply it by its own activity. Now notice what he has done here. For the capacitance of the logic, we have how many number of devices we have 50 million. Okay, so 50 million what? 50 million transistors. Every transistor of those has 12 lambdas. He told me right here. Okay, so bring down this one here. Okay, and I know that every lambda from this process in this textbook is 25 nanometer, okay, which is 0.025 micron. Okay, now that will convert number of transistors into what? Into micrometer. Then every micrometer provide for me 1.8 femtofarad. I multiply all of that, I end up with 27 nanometer. I repeat the same computation for the memory, but now the number of devices 950, okay, million. For lambda, why it's different? Well, because the memory sizes for the transistor, the average is 4 lambda, and 0.025 is the same, and this one the same, and I get 171 nanofarad. Now, then I multiply, go back here, okay? Let's see if I can pick a different color here. Now, let's see, we needed the activity factor and capacitance. So the activity factor for the logic, 0.1, where is it? Right here, okay? Right here, okay? 0.1 times the capacitance for the logic, 27 nanofarad, plus the activity factor of the memory, 0.02 times the C for the memory. Multiply that for V square times frequency, you end up with 6.1 watt per, as total dynamic power for this chip. And now we will talk about the reduction of power and how we reduce the dynamic power. Um, we'll stop here and continue the discussion in the next class.